Welcome. In this session, we learn the concept of charging of a capacitor. Let's start. Now, to learn the concept of this charging of a capacitor, let's take a simple example of a circuit that has R and C. So let's take this example of RC circuit. And our goal is to learn, if we connect a source to this RC circuit, what is the behavior of the voltage across this capacitor? What will be the behavior of the voltage across this capacitor as we connect a source to this? So let's suppose we are connecting a source to this RC circuit. Means we are connecting, suppose, a battery to this RC circuit at t equal to 0. Let's take this very simple and let's see what will happen to the capacitor voltage as t increases. And as the time progresses, what will happen to the voltage across this capacitor? All right, and let's assume the voltage across the capacitor at Vc of t is equal to 0 for t less than 0. For t less or equal to 0, the voltage across this capacitor is 0. In other words, the initial charge or the initial voltage across the capacitor is 0. All right. So to do the analysis of this circuit, we'll redraw the circuit. We'll draw the circuit that's valid for t greater or equal to 0. We know the voltage across the capacitor for t less than 0, 0. So that's already determined. Now, what will happen to the capacitor voltage for t greater or equal to 0 when we connect to this source voltage? So let's redraw the circuit. So the circuit that's valid for t greater or equal to 0 is this. So now we are connecting this switch. And so this is our battery V of S, this is R, this is C, and our goal is to observe Vc of t for t greater or equal to 0. Now, in the previous session, I already discussed it. This switching action can be represented by this this unit step signal. All right. So you can also do this. Means you can draw a general circuit which is valid for all time and replace V of S by V of S U of t. All right. Now let me do it like this. All right. So now the voltage across this capacitor. So let me to do this to observe the behavior of this capacitor voltage as we connected the source to this. So this circuit is valid for t greater or equal to 0. Now to observe this voltage, let's use the KCL at this point. Let's apply KCL at this point. All right. So the let's suppose the current, because there are two branches, so there will be two currents. So the current that goes here is suppose I1. Suppose that the current that leaves in this branch through this branch is I2. So using KCL, what we have? So using KCL, we have I1 plus I2 should be equal to 0 because I1 is leaving, I2 is leaving. So the sum of the currents should be equal to 0. This is the statement of KCL. Now, what's I1? I1, as you can see, is the current that flows through this resistor. Now, what's the voltage across this resistor? This R. The voltage across this resistor is Vc. This is Vc, this is not this. This is Vc of t, yes. This is Vc minus Vs, right? This is the voltage across this capacitor because on this side, the voltage is Vs, on this side, the voltage is this, and we are assuming the current is going in this direction. So that means Vc must be at higher potential. So I1 is equal to Vc of t minus V of S divided by R. This is the current I1 plus what's I2 is the current flowing through this current that flows through this capacitor, and we know the current that flows through the capacitor is given as this C dV by dt is the current that flows in the capacitor. So this is the capacitor current. So the total sum of the currents is equal to 0. So or we can write it like this. We can say or can say C dvct by dt plus Vc of t by r is equal to Vs by r. All right. So what I have done, I have taken this on the right hand side. That's what I have done. So this is the differential equation that governs the behavior of this voltage across this capacitor for t greater or equal to 0. For t less than 0, the voltage across the capacitor is 0. So we must know how to solve this differential equation. Now have a look at this differential equation. If R and C are constant, if R and C are constants, then this differential equation is a linear differential equation. Linear differential equation. So how do we solve a linear differential equation? All right. So we know the form of a linear differential equation is, if I say dy by dt, where y is a function of time, is equal to py is equal to q. This is the general form of a linear differential equation. So what we do, we multiply this equation. How do we solve a linear differential equation? We multiply this differential equation both sides by the integrating factor. What's an integrating factor? The integrating factor of this linear differential equation is equal to e raised power integral p dt. What's p? P is this. Now let's bring this differential equation, the differential equation that governs the behavior of the capacitor voltage, in this form. All right. So let's bring it in this form. I can write this above differential equation that we obtain like this. We can say it is t Vc of t by dt plus Vc of t divided by Rc is equal to Vs of t divided by Rc. Have a look. What I have done, I have divided both sides by C. That's what I have done to this differential equation. Now have a look at this differential equation and this differential equation. They are identical, where Vc of t is equal to y and p is equal to, here p is equal to 1 by Rc, q is equal to Vs of t Rc. So to solve this differential equation, what we are going to do, we are going to multiply it by the integrating factor. Now what's the integrating factor here? What's the integrating factor for this differential equation? The integrating factor will be simply e to the power of 1 by Rc dt. And what's this equal to? It will be simply e to the power of t divided by Rc. Have a look. So this is the integrating factor for this linear differential equation that governs the behavior of our capacitor voltage. All right. So multiplying both sides by this integrating factor, what we'll get e to the power of t by Rc dvct by dt plus e to the power of t by Rc Vc divided by Rc is equal to e to the power of t by Rc Vs of t divided by Rc. All right. Now have a look at the right hand side of this equation. We can write the left hand side of this differential equation. We can write it like this. We can say it is the differentiation of e to the power of t by Rc Vc of t. Have a look at this. If we use the product rule of differentiation, it will be first will be as such, then differentiation of this, that is this component. Then the second part will be this will be as such, differentiation of this. What is the differentiation of this? E to the power t by Rc divided by Rc. Have a look. So this will give you back this. And on this side, what we have, e to the power of t by Rc divided by Rc Vs of, sorry, Vs is not a function of time. It is a constant voltage. So Vs is not a function of time. So it is simply a battery voltage. All right. So I have written it wrong here. All right. So Vs is not a function of time. It's a constant value. Now integrating both sides. Integrating both sides, what we'll get? We'll get integrating here, and we'll get a constant of integration. All right. After you do this integration step. So this differentiation and integration will cancel. And there will be dt, there will be dt, and dt cancels, this cancels with this. So we'll have left with e to the power t by RC Vc of t, that will be equal to Vs by RC e to the integration of e to the power of t by RC dt plus constant of integration. All right. Now this will be equal to e to the power of t by RC Vc of t, or this is equal to Vs divided by RC. What is the integration of this? E to the power of t by RC divided by 1 by RC. Now you can see here 1 by this RC and this RC cancels here, and there is one more term, that is plus k. All right. So what we have obtained from this, we have said or e to the power of t by RC Vc of t is equal to Vs e to the power of t by RC plus k. Now what's our aim? Our aim is to obtain Vc of t. So dividing both sides by e to the power of t by RC, what we'll obtain? We'll get e to the power of Vc of t, we'll get Vs plus k times e to the power of minus t by RC. When you divide by both sides by e to the power of t by RC, this will get cancelled, this will get cancelled here, and here we'll have e to the power of minus t by RC. All right. Now, what's the value of this constant of integration? How we obtain that? We put t equal to 0. Put t equal to 0 here. What we'll get? Vc of 0 is equal to Vs plus k times e to the power of 0. E to the power of 0 is 1. All right. Now, what is Vc of 0? We said this, the value of the capacitor voltage at t equal to 0 is 0 because the capacitor is not charged initially. So then this will be equal to this. Then k will be simply, you can say, or k is equal to minus V of s. Now substitute it back here. We'll get Vc of t is equal to Vs minus Vs e to the power of minus t by RC. So this will be equal to Vs into 1 minus e to the power of minus t by RC. All right. So this is the capacitor voltage for t greater or equal to 0. So this is the value of the capacitor voltage for t greater or equal to 0. So the capacitor voltage is for all time, we can say capacitor voltage is equal to 0 for t less than 0, and for less or equal to 0. For t greater or equal to 0, the capacitor voltage is equal to V of S 1 minus t by RC, and this is for t greater or equal to 0. So this is the capacitor voltage for t less or equal to 0 and t greater or equal to 0. All right. So this is the capacitor voltage, and we can write it by a single equation. We can say the capacitor voltage simply is Vc of t is equal to Vs 1 minus e to the power of minus t by RC if we multiply it with u of t, right? So how we can write this? Because we know u of t is 0 for t less than 0, that makes Vc of t equal to 0, that's this part. For t greater or equal to 0, this is equal to 1, so that will give us this second part. All right. So this is the capacitor voltage in general. When you connect a source to an RC circuit, the capacitor voltage looks like this. All right. Now, if we plot this capacitor voltage, how does the plot look? So let me plot it. If I say this is the time axis, and this is the amplitude axis. All right. Now the input is 1. Sorry, input is V of S for t greater or equal to 0 because we are connecting the switch like this. So this for t less than 0, there is nothing connected to this, and also the capacitor voltage is 0. We are assuming the capacitor initially relaxed. Initially relaxed means it's not charged, means there is no voltage stored in the capacitor. All right. Now, what's the behavior of this equation? If you plot it, this expression, if you plot it, it looks like this. The capacitor voltage rises like this. Okay, means it increases like this and finally reaches to this uh, this Vs, depending upon how long you have connected this source to this RC circuit. So capacitor voltage rises like this and finally reaches to the source voltage if you give it enough time. All right. So this is the behavior of the capacitor voltage for t less than 0 and for t greater than 0 when you connect a battery to a RC circuit. This is how the capacitor voltage changes. So it takes some time for this capacitor voltage to reach to the source voltage. All right. Now, how much time it takes and how do we get this behavior? We'll discuss it in the next class. But I hope you have got it. This is the behavior of this is the capacitor voltage when you connect a source to this RC circuit. So in short, you must remember this. The capacitor voltage behaves simply like V of S. This is the battery voltage, e to the power of minus t by RC U of t. All right, this is the behavior of this capacitor voltage if you turn on this switch at t equal to 0. All right, this is very, very important expression. Now, in the next session, what we are going to do, we are going to learn if the capacitor is already charged to some voltage, how does it discharge? How do we discharge this capacitor? That we are going to see in the next session. All right, let me stop here.